Thank you very much. So it's going to be a very interesting session this afternoon, and we start with Andrew Howard from Caltech with the initial performance results from the Keck Planet Finder. Andrew.
All right, it is great to be here. I am going to tell a 9-year story about the development and initial results from KPF. This is a story that involves contributions from more than 100 people, so I hope that I can represent them well. KPF, like many of the instruments that we've seen so far, is a cross-dispersed optical shell spectrometer. It lives on the summit of Mauna Kea. It's connected to the Keck 1 telescope. KPF is built on a platform of zero-dur glass that makes it extremely immune to temperature changes. Also, the size of the Keck 1 mirror, 10 meters in diameter, will give KPF some extraordinary powers to look at faint stars that have some of the most interesting planets, as well as to do ultra-high resolution spectroscopy. So let me briefly just walk you through some of the specs for KPF. I'm not going to read every line on here, but I feel it's important just to get some of the basics out of the way. So KPF spans 2 channels. We call these the red and the green channel. They have different cameras, but share a common shell grating. We achieve a resolution of about 95,000 in one camera, about 98,000 in the other. We have a separate ancillary spectrometer to measure the calcium H and K lines, which are an important index for chromospheric activity, but we focused instead the main KPF bandpass just a little bit redward of that, which allows us to push down to get some important regions of spectrum for the M-dwarfs. The capabilities of KPF, we've designed it with a goal of 30 centimeters per second instrumental precision. This is a goal for precision over all time scales. We're already in many ways exceeding this on short time scales. We haven't yet had the opportunity to try it on longer time scales, but that will be an important test. We want to do precision radial velocities down to 14th and even 16th magnitude. This will enable follow-up of thousands of Kepler systems that have exquisite timing and radius information, but not yet the value added from mass measurements from Doppler radial velocities. So I'm really excited, especially to see that science. Because we have this 10-meter telescope and very high throughput, we can do ultra high resolution spectroscopy, which is going to be important for the 10 centimeter per second era. A 10 centimeter per second measurement from a spectrum requires a signal to noise of 600. This is pretty high, and we think that KPF will be a great tool to start exploring how we can make those measurements. So here's an image of KPF. This is about 1.5 years ago when it was being built here in California. It doesn't usually glow red like this. There's some lights below. This is an artistic photo. You can see the light is propagating up through the zero-dur glass that gives KPF its great stability. And in addition to the base of the spectrometer, the optics and their mounts are also made out of this zero-dur material that happens to have a coefficient of thermal expansion, which is a part in 10 to the 3 or a part in 10 to the 4 better than most metals. This is a zoom in on one of the interfaces of one piece of zero-dur mating to another piece of zero-dur. We went through years trying to figure out how to engineer these interfaces so that we wouldn't have to use any glue or metals or anything that would dominate the thermal expansion budget. But we figured out how to do it. Here's an example. One of the other key components of KPF is the fiber injection system. And this is a CAD model of what the fiber injection system looks like. So we receive a beam from the Keck 1 telescope that bounces off of a fast tip tilt mirror that allows us to trim up our guiding. The light is then split into 3 wave bands. The ultraviolet feeds a fiber that goes to the calcium H and K spectrometer. The main band pass goes into an octagonal fiber going to our primary spectrometer, and then we guide in J band. So this fiber injection unit design has some advantages. Mainly, we can use all of the light in J band to do guiding. A challenge is that they're different focal planes, and figuring out how to match those focal planes and their 0 points, scales, offsets has been a challenge. So far we're achieving about 25 milliarc second guiding precision, but our accuracy is maybe at about the 200 milliarc second level, and this is something that we're working to improve on. So one nice thing about this talk is I don't have to only show CAD models. I can show actual built hardware. So here's our real fiber injection system. This is the first bit of hardware in the fiber train that this is connected to is our mechanical agitator. This is a device which gently taps on fibers in little enclosed tubes to mechanically scramble the modes in the fiber so that we have very high spatial uniformity in a time average sense for these multi-mode fibers. We also have a double scrambler. This is a somewhat standard device. The double scramblers in KPF allow us to penetrate into the vacuum chamber in a collimated beam, and they, coupled with the octagonal cross-section fibers in KPF, which are used on other instruments too, we achieve a scrambling efficiency in near field and far field of about a part in 10,000, or perhaps a little better. We're using a really big telescope. We don't want to have a really big spectrometer. The way we get around this is by slicing an input image that's already been stabilized because it's gone through this fiber system. So we have a device we call the reformatter that slices the science fiber of KPF into 3 slices. Here's a set of resolution elements from a laser frequency comb spectrum, and you can see the calibration trace, 3 science traces, and our sky trace as well. We model the science traces completely independently because they have very slightly different wavelength solutions. So last thing I'll show you about KPF before we actually ship to Hawaii, we did a series of tests to assess its stability. This is one using Thorium-Argon. We've also done tests like this using the laser frequency comb. So over a period of about 10 hours, we injected Thorium-Argon light into all of the fibers of KPF. And then we measured the drift of each of those fibers in an absolute sense and in a relative sense. And you can see the absolute drift when we had very poor thermal control was on the order of 10 meters per second, maybe 15 meters per second. But the lines are all right on top of each other. And if we simply subtract the cal drift measurement off of the science drift measurement, we're left with flat lines that have scatter of about 17 centimeters per second, which we think are the photon limited errors because we happen to be using Thorium-Argon. When you bin those measurements, we get down to 6 centimeters per second. And if you compute the Allen deviation, we find that you can't bin down forever, but we're able to bin down, at least for this data set, down to something like 4 centimeters per second. So this is not a promise that this is the ultimate stability of KPF. These deviation plots can turn up if you're not careful. And so it's our challenge to try to operate KPF in a way that maintains the stability for long time scales. So KPF arrived last summer at Keck Observatory in a pair of shipping containers. Our group unpacked and completely reassembled the spectrometer, which of course had to be put in separate little protective shells because the main spectrometer components are made of glass. You can see it's reassembled mostly here on the right. We have a device that we call a solar calibrator. This is the work of Ryan Rubenzahl, who has a poster on this. And the solar calibrator injects sunlight into a pair of optical fibers that go into our calibration system. And we will be able to use, hopefully starting in a week or so, to measure sun as a star velocities and spectra. First light for KPF happened in November of last year. It was a glorious event. Most of the people that are in this picture are here in the audience today, and it was wonderful to have them at both locations. We chose to observe Jupiter as our first target, not because I'm imagining Jupiter will be a major target for KPF science, but we really like the poetic aspect of observing a star in our own solar system with an instrument that's designed to detect planets in other solar systems. KPF now has a measured on-sky throughput, which is about what we expected, slightly higher at many wavelengths, and it's quite high overall. So in good seeing, we get 8 to 10% throughput from the top of the atmosphere down to the CCDs. We've also measured the resolving power using the laser frequency comb and achieve about 95,000. Our on-sky tests for Doppler stability for KPF are also at the level that I would say are extremely encouraging on short timescales, but we don't yet have information on longer timescales. So on the shortest timescale, we've observed tau Ceti for a bit more than an hour, and we when you bin those measurements on a p-mode timescale where we expect natural oscillations, we see that these measurements bin down to about 23 centimeters per second. So again, this is extremely encouraging, but is not yet a demonstration of KPF's kind of stability over all timescales. On somewhat longer timescales, using a different star called HD 55575, also known to be a Doppler standard star, we visited it 6 times over 2 different days, separated by 4 days. And you can see the velocity RMS is highlighted in red there. It's 37 centimeters per second and 66 centimeters per second. I wouldn't put great stock in precisely those values, but what this tells us is as we increase the time baseline, we see that KPF is able to maintain its stability, and we're going to work to do that for longer and longer timescales. So last 2 slides. This is at this EPRV conference, we try to air some of the challenges that we have and things that we're working on. KPF is very much still a project which is not complete. We have several things which I'll enumerate that we're working on. Our on-sky commissioning is going to last at least a couple more months. Somewhat terrifyingly, we also have science observations that are beginning in 2 weeks. These are science observations that are mostly Rossiter-McLaughlin events, but starting in a couple months, we're also going to have time series measurements as well. So some of the challenges we face is that while in principle, this is a simple instrument, there's no moving parts inside the spectrometer, it's extraordinarily complicated. There's 12 different subsystems. They all have their own servos and control loops and calibrations and computers, and they all have to talk to each other in a reliable and automated way. Our calibration system is similar to the ones employed by other groups. We have an LFC, an Etalon, and a Thorium-Argon, and they have their own challenges, which I've listed on the slide. We've also had some trouble figuring out how to reliably operate the liquid nitrogen control systems for the cryostats that cool the CCDs. Last slide, some remaining tasks, and we're hoping to execute some of these in what we call a service mission. So we haven't yet actually built the thermal enclosure around the KPF vacuum chamber. We've just relied on the fact that the room that it's in is moderately stable. We're going to do that in a handful of months. We have an issue with the vacuum ion pumps they're emitting some light of their own, and we have to figure out how to baffle that so that we don't see ion pump light on very long exposures. And we have 2 misalignments that we hope to correct during a service ignition, and these have to do with the optical slicer is one of them, and the second is our green CCD is very slightly out of the focal plane, and so we're losing a little bit of focus on one edge of the detector. So I will stop there and take your questions.
Thank you very much. Questions from the audience? Yes, Jen.
Oh. Kind of says what.
This misalignment, you showed Jupiter here. You showed Jupiter. Great talk, by the way. Thank you very much, and looking forward for more data. Yes, the last slice, the spectrum is a little bit off.
So I'll tell you, this actually terrified me while it was happening. There were 100 people, 30 in person, another 70 on Zoom, and we're doing this live, and I was narrating it. We point at Jupiter. We have 3 science slices and 1 sky fiber, and those 2 fibers are displaced from each other. And I'd seen these spectra come in, and our sample spectra, they all come in perfectly aligned. You can see here that this is not aligned, and so I had about 3 seconds of panic. Maybe we broke KPF on the first observation. And I hope that it appeared more like a dramatic pause, because then I realized that Jupiter is in fact rotating, and the 2 fibers are on different parts of the rotating disk. So we observed a Doppler shift in Jupiter.
Great, great measurement. Other questions? Yes, Dennis.
On a slide, you showed a super high signal noise ratio mode of 2000. So how is that achieved, and what are the limitations?
It's achieved because we have higher cross dispersion than most instruments. Each of the 3 science slices spans 15 pixels in cross dispersion. So in total, there's 45. The CCD well depth is deeper than is typical. It's about 150,000 electrons. You asked about the limitations. I think at that level, we have to develop a linearity correction. We have a lot of the data for that we did in laboratory testing. We haven't yet implemented. I think there's other effects like the brighter, fatter effect and charge transfer efficiency that are going to be limiting. Those are things where we've taken a bunch of data in the lab with the fingers crossed that we're going to be able to calibrate it out, but that's work yet to do.
Okay, thank you. Then I will go to the next talk. Thank you very much, Andrew.